Okay, so with molecular orbital theory, we have the ability to rationalize how we can take atoms and convert them into molecules. And MO theory is incredibly important because it's foundational. So starting with the atomic orbitals and working our way into molecules. Now, right now we're going to focus on, again, just 2 atoms. But you can apply molecular orbital theory to polyatomic species, to 3 atoms, 4 atoms, 100 atoms. In chapter 3, we'll open up an aspect of symmetry, where what you do is you relate a group of atoms together. That way you can simplify the model that you're working with. But something we're going to find that molecular orbital theory does not tell us is anything about the shape of the molecule. So if we have 3 atoms or more, now we start getting into geometries and so forth. So we're gonna see that we have to kind of go back and forth between different types of bonding theory to explain it. Before I switch gears, I want to go over a couple more molecules with MO theory. Carbon monoxide. So with CO, you should end up with this. And we're going to see that the MO diagram is going to be consistent with this. So if I've got carbon over here, oxygen over here, so that's 2p. And even if I don't write it explicitly, anytime you have an MO diagram, again, it's always with respect to energy, right? So energy is going up. The more electronegative element, the atomic orbitals tend to be at lower energy. So I'm drawing it a little bit askew, but again, these are details you can find in a given book. So we've got our sigma, our pi star, and sigma star. It's always a good idea, write the atomic electron configuration off to the side for each of the atoms. And just a, of course it's dead. And again, sometimes you'll see these as straight lines or dashed or whatever. It's just to show some relative connectivity of how the orbitals mix. I'm leaving off the 2p and all that because it's kind of understood. So carbon, 1s2, 2s2, 2p2. So that means we're going to have 2 electrons there, and oxygen, 1s2, 2s2, 2p4, right? Again, look at our electron configurations. So now we've got 4 electrons. 1, 2, 3, 4. You could skip the step of putting them in to the atoms first, but I think it's a good habit to do that. So we now have a total of 6 electrons that we're going to put into our MO diagram. Again, what about the 2s shell? What about the 1s shell? They would be at lower energy and they would be completely full. So they're not going to participate in any chemical bonding. So we don't need them. In other words, you can put it in here, but what would happen is you'd have 2 electrons in bonding, 2 electrons in anti-bonding, which cancel out. So they're there, but they're not participating. So we have 6 electrons total. So 1, 2, we go, again, low energy, off-bow principle. 3, 4, 5, 6. And again, for calculation of bond order, our bond order is 1/2 of the bonding electrons, which would be 6, minus the anti-bonding, which is 0. So we have a triple bond. That's consistent with the Lewis dot structure. And our Lewis dot structure tells us this should be diamagnetic, and that's what we observe here as well. And that's what's experimentally observed. So diamagnetic. So this is an example where our Lewis dot structure and our MO diagram are completely consistent. But something we're going to be able to use MO theory for later in the course, I'm just going to kind of tease it right now, transition metals. We have the D block elements, and those elements, along with interacting with atoms, so for example, you can have iron with chloride, right? You can have iron with oxygen. In some cases, you can have iron interacting with an entire other molecule, right? How is that possible, right? For example, carbon monoxide, when you breathe it, it's poisonous, right? It's somehow interfering with your ability for respiration. And what we find is iron is a transition metal. I'll draw it this way. Actually, do it right. And it has d orbitals. Now we're going to come back a little bit later and go through the all 5 d orbitals and their relative positions and so forth. The d orbitals. So let's make, blue is positive phase, that's fine. And then red is negative phase. So this is one of our d orbitals. It basically looks like a clover leaf. Okay. If we have carbon monoxide, so here's carbon, here's oxygen. We observe that the carbon is actually what's bonding to the iron. Now you can make a rationalization that it's donating these 2 electrons, but that doesn't explain the strength or character of the bond between carbon monoxide and iron. What's observed both experimentally and we rationalize it with theory, well, carbon monoxide, it's donating these 2 electrons, so we've got this d orbital. Look what else we have on carbon monoxide. We have these pi star orbitals. We have anti-bonding orbitals, but they're empty. The way we could graphically represent the anti-bonding orbital on carbon monoxide is we have a lobe of positive phase. I'm drawing it centered on carbon just because the carbon is pointing here, but we could draw it across the entire molecule with the same result. Okay. Now, by itself, if I just look at a pi star orbital on carbon monoxide, it is anti-bonding with respect to carbon monoxide. So if I add another electron here, I'm reducing the bond order. That make sense? Okay? But in free carbon monoxide, it's empty. Okay? So it's not changing the bond order. But look what happens. If we have carbon monoxide and it donates some electron density, I'll draw it bigger. If it donates some electron density to a metal like iron, well, guess what? Metals really don't want to be negative. Iron does not want that electron density. So it's going to look for a way to get rid of it. Look at the symmetry of the orbitals. And what I mean by symmetry is phase. Right? Go back all the way to the beginning of wave math. We have a wave in phase, or a combination of 2 waves in phase. What happens, right? They get bigger. Right? Positive phase, negative phase, negative phase. So this orbital combination of the anti-bonding with the d orbital. So again, this is a d orbital. We'll come back and look at all. So there are 5 d orbitals. 3 of them look like clover leaves that are on the diagonal, and one of them is a clover leaf that is on the XYZ axis. It's actually in the XY plane. And then the other one basically has a donut and a set of lobes. But right now we'll just look at the diagonals. So this is one of those 3. It has the correct phase that it can interact with the anti-bonding orbital. So again, what I'm drawing right here, this is a pi star orbital. How many pi star orbitals is that? It's 1 with 2 lobes, right? Remember, in other words, you can have 2 lobes that define an orbit. It has the same phase, and as it turns out, it has compatible energy with the iron. So if you have the right phase and you have the right energy, you can get an overlap of the orbit. Well, look what's going to happen. Carbon monoxide is going to donate electron density to the iron. It's good, because again, a pair of electrons. The iron doesn't want that electron density. So guess what it's going to do? It's going to actually give it back to the ligand. Some of that electron density goes into the pi star orbital. Okay? Which, again, seems very odd, but we have very good experimental evidence of this happening. If you have carbon and oxygen with a triple bond, okay, those 2 atoms are held together very tightly. Now, measuring the bond distance is actually a little bit tricky. It's possible to measure the change in bond distance, but we have this thing called infrared spectroscopy. For those of you taking organic, right? You IR, right? When you have an IR of free carbon monoxide, it's at very high energy, around 2143. And we will come back to this when we get to symmetry. So increasing energy is this way, okay? And this is about 2143, I believe, wave numbers, which is reciprocal centimeters. If you don't want to quote frequency, what you can do is you can take wavelength and then invert it, and now it becomes frequency, but you're using length, but it's reciprocal length. Again, it's a kind of a tricky physics way of not having to say it's 7.93 whatever hertz and so forth. So that's higher energy. That's free carbon monoxide. So this would be free carbon monoxide gas. When the carbon monoxide is bound to the iron, it drops in energy to about 2,000 reciprocal centimeters. We'll see the spectra can actually be a little bit more complicated, where instead of 1 peak, you get multiple, but here we'll keep it simple. In free CO, we've got a triple bond, okay? What physical analogy is often used to describe how electrons are holding 2 atoms together? Is anybody who's not a physics major?
Like a magnet?
Not a magnet, a physical thing.
Like gravity?
So think in terms of an object, something physical. Got 2 atoms.
Is it gravity?
It's not gravity.
Like a bridge?
You're on the right track. Springs. In other words, they model the atoms oscillating back and forth using what's called Hooke's law, which is for a spring. Okay? So what it means is, if I have 1 spring, or actually let's go with 2. If you have this compound, Okay, what's the name of that functional group? Very good, ketone. So this is a ketone. This has an infrared energy around 1730 reciprocal centimeters, somewhere in that ballpark, plus or minus a little bit. If you only have two springs, you're at lower energy. What you're looking at is the oscillation of the carbon and oxygen atom. So if there's one spring, it's a very slow oscillation at lower energy. So CO in ether would be way down here. A double bond is slightly higher energy, and a triple bond is the highest, right? So if the bond order is dictating how we have this oscillation, what's going on when we bind the CO to the iron? What's happening to the bond order? It's decreasing. Why is it decreasing? Exactly. So what's happening is carbon monoxide, when it's all by itself, has a triple bond. But when it interacts with the metal, it donates electron density, which actually gets put back into its own pi star. The pi star is anti-bonding with respect to the CO. So it's actually negating its own chemical bond. What it's doing is it's strengthening the bond between carbon and iron, but in the process of doing that, it's weakening the bond between carbon and oxygen. So as one bond gets stronger, the other one gets weaker. Does that make sense? It's a little, again, a little bizarre, because this is not what you're used to seeing as far as chemical bonding. You've been taught, here's a molecule of ammonia. It's a happy molecule, that's all it does. But we're going to see that those molecules can bind to metals. Yes?
This is the pattern for most bonding atoms and molecules, not just...
Well, we're going to see this type of what's called pi back bonding, this interaction, is specific for transition metals. The only way to rationalize it, the only way to understand what's going on, is to understand MO theory. So later in the semester, when we start talking about transition metals, we're going to refer back to molecular orbital theory. That's why I want to show it to you now, to show you that MO theory has a point. In other words, there's a reason why you need to know it. Because, again, you breathe carbon dioxide, and it's fine, because your body's literally making carbon dioxide. You breathe carbon monoxide, well, what happens? You die, right? And it's because the CO binds to the iron very strongly. That's the problem. That's why carbon monoxide is a poison, because that interaction, that pi back binding, this filling the pi star, is very favorable, so that carbon monoxide wants to bind to the iron, and vice versa, stronger than water or oxygen or CO2. So, write it out. So this phenomenon is referred to as a pi back bonding interaction. We will come back and have a much more detailed discussion of this when we get to the transition metals, because what we're going to find is water can interact with iron, but water does not have a pi system, right? In other words, water is just this, right? Well, if you don't have pi bonds, if you don't have double bond or triple bond, you can't have pi back bond, right? So in other words, we're going to be able to explain why a molecule of water can interact with iron in one way, but then when we start having molecules like carbon monoxide, or this molecule, what's this called? Cyanide, right? Why would I pick cyanide? Well, look at the Lewis dot structure of cyanide. Obviously, you've got a -1 charge up here. The -1 is actually, we be more formal. The -1 is actually in carbon. Cyanide is isoelectronic with carbon monoxide. If I change this to oxygen and add a negative charge, they have the same MO diagram. So cyanide and carbon monoxide, from an electronic point of view, are identical. Okay? Well, what do you know about cyanide and ingesting it?
It's bad for you.
It's obviously bad, it's poisonous. And it's the same mechanism. In other words, cyanide will also bind to your hemoglobin incredibly strong for the exact same reason, because it has this pi bonding interaction. So what you find is a lot of things that are related to biochemistry, you can actually start to explain it through inorganic chemistry, because you've got a metal in there. If you didn't have a metal, that would be different. You know?
I have a question.
Yes?
Is CO an inorganic compound or is it organic?
That's an excellent question. Is carbon monoxide organic or inorganic? The term organic is basically referring to life. So technically, no. Now, is organic chemistry really chemistry? Obviously, yes. But the designation of chemistry and life, that's where you start getting into trouble. Because, spoiler alert, there is no biology. It's chemistry run amok. So, in other words, can you have a lot of chemistry without amino acids? Or a lot of can you have biology without amino acids? Amino acids are just stupid little molecules. I say that because when I was taking, I lasted 1 day in biochemistry. The professor said, memorize the 20 amino acids. I said no. I dropped the class and became an inorganic chemist. So the thing is, and that's actually a very good question, because that designation of what we call organic. So, for example, is diamond organic? Because diamond is all carbon, right? And if organic chemistry is carbon, then diamond should be organic chemistry. But of course, there is no life associated with diamond, right? In other words, see, that's the history of organic chemistry, that it was assumed that you had to have some type of plant or animal that would make the molecule for organic chemistry. But now we know that's not true. See, that's why I say that designation of calling something organic is not really relevant, because again, we can make aspirin using compounds that were not associated with life in any shape, form, or fashion. Right? And aspirin you can also get from a plant. So going back to this, we have iron, and it's interacting with another molecule very strongly. But the only way to explain it is we have to go back and look at the MO diagram and realize these d orbitals that we'll be talking about are actually interacting with these pi star orbitals. So in the molecule of CO, when it's free, when it's just in the air, these are empty. But when it interacts with the iron, then it becomes partially populated. Not fully populated, but partially populated. And that's enough to start forming very strong chemical bonds. And some of the evidence of it, we can find it in, like I said, in the infrared spectrum. If there was no pi back bonding interaction, in other words, if this was not happening, we would expect the carbon monoxide, its infrared, should be up here. It should be closer to the free CO. But what's observed is that it moves to lower energy, which corresponds to a weaker chemical bond. Okay? And this is something that we'll be able to use the infrared to determine the bond interaction of the carbon monoxide with the metal as we go and start looking at this type of chemistry. And before I leave carbon monoxide, let me just go ahead and let's do the MO diagram of cyanide to make that point. So, because I don't think we've done any charged molecules. Well, okay, take that back. We did a couple cations. So, sigma, pi, star, sigma star. And as I, somewhat mock biology, biochemistry, there's an entire field called bio-inorganic chemistry, where you look at exactly this type of thing, of something like hemoglobin, which has an iron in the center, right? And then it has the organic molecule around it. Same with chlorophyll and so forth. In fact, in your textbook, if you're more interested on the biochemistry side than the inorganic, I would suggest skip to essentially the last chapter of the textbook and flip through the bioinorganic section, and you'll see, oh wow, look, there's inorganic chemistry in my biology. Electron configurations, just write them again. So 1s2, 2s2, 2p2. So we're going to have 2 electrons here. 1s2, 2s2, 2p3. 1, 2, 3. But now what we have to take into account is charge, right? Cyanide has a -1 charge. Okay? It doesn't matter which side. So if we, slap one more electron in there, that gets us to a total of 6. So neutral CN has 5 electrons in P. That's not going to work, but we get -1. And 1, 2, 3, 4, 5, 6. We're going to have a bond order, again, 1/2, 6 minus 0, which is 3.0. And of course, it's going to be diamagnetic. And the other very important takeaway, if you didn't know what the atoms were, and you just looked at the electron configuration, if you just looked at the MO diagram, CO and Cn-1 are identical, right? So what that means is carbon monoxide and cyanide are isoelectronic. Did you hear this term used in Gen Chem?
No.
You should have. Fluoride, F-, is isoelectronic with neon, right? They have the same electron configuration. We can apply this to molecules. So isoelectronic means we have 2 or more things that have the same electron configuration. They're not the same chemically, but we find that they often behave very similar. For example, cyanide and carbon monoxide are both very toxic, right? So in other words, if you get cyanide in your body or carbon monoxide in your body, the mechanism of how it attacks your hemoglobin and so forth are similar. A very significant difference, of course, is, well, cyanide is an anion, so it would have to have a cation. So it would have to be potassium cyanide or sodium cyanide, whereas carbon monoxide is in the gas phase. Okay? But again, from an electronic point of view, they're identical. Okay? And isoelectronic can be for atomic or molecular species. Right over here. So kind of using neon as our reference point. Okay? Fluoride, neon. Fluoride would be isoelectronic with neon, right? We gain 1 more electron. And sodium +1 would also be isoelectronic with neon. fluorine, neon, sodium are three different elements, but as the anion, neutral, and then the cation plus one, electronically they're indistinguishable. Right? And we know this in Gen Chem, well, most of the main group elements, they want to gain or lose electrons to be like the noble gases. So we're going to see a similar phenomenon with molecules, that many molecules will be isoelectronic because that's the lowest energy electron configuration to have, right? So CO and cyanide, for example. Is bromide, excuse me, is bromide isoelectronic with neon? No, technically no. It's similar. You want to say yes because it's got a noble gas configuration. Bromide would be isoelectronic with krypton, Kr, right? Not neon. Yeah, they're in the same family, the same group, so they'll be similar, but they would not be isoelectronic. Okay? And again, this is something that I even see chemists make that mistake because it's really glossing over where you say carbon and silicon are isoelectronic. No, they're not. They're in the same group, they can have similar chemistry, but isoelectronic means that it be identical electron configuration. So again, neon, argon, krypton, xenon, they're in group 18. They all have the closed shell, but they are not the same number of electrons. They are not the same configuration. So again, it's one of these things where you're not in a 111 course anymore. So you need to know these kind of subtleties because not. It will have a closed shell of the noble gases, but like I said, it's not going to be isoelectronic. Now, with molecular orbital theory, as you might guess, we're scratching the surface. There's so much more we could do with it, and for explanations of different aspects of chemical bonding. And we will come back to it. In my course, we're going to focus more on the transition metals and how they react with atoms and molecules, and see how we can start applying aspects of molecular orbital theory to it. If you took an organic chemistry course, the aromatic rings that are in benzene and naphthalene and things like that, that actually is also part of MO theory. The difference in organic, especially when you just take like the 301 course, is you're only looking at the bottom of the MO diagram. You don't look at the anti-bonding combination. So you see the donut, but you don't see the negative version of it, the anti-bonding version of it. And again, in a field called organometallic chemistry, which we'll be covering later, the only way to really understand how these groups of atoms are binding together is to have, like I said, a more sophisticated understanding of chemical bonding than just, again, Lewis theory. So, with MO, like I said, with MO theory, we will be coming back to it in time. In fact, now we're going to switch gears and we're going to start talking about geometry, shapes of molecules. A little bit later, we'll talk about some aspects of solid state chemistry. And to explain things in the solid state like semiconductors, how lasers work, how computers work, and so forth, that's actually based on MO theory. But instead of two atoms, now you're looking at combining a mole of atoms, right? In other words, 6 to the 23rd or more. But it's the same thing. Now, an MO diagram gives you the electron configuration. You can determine bond order. You can determine is it paramagnetic or diamagnetic. And that's really it. Even if you have an MO diagram of, say, benzene, it won't tell you that the benzene is in the shape of a hexagon. So we're going to see molecular structure rationalizing that, we kind of have to switch gears and go back to Vesper theory, right? So. Grab a pair. Go. So Vesper. In a molecule, we would predict that as we form chemical bonds, the electrons within those chemical bonds want to repel each other, right? And they're going to form geometries with the greatest amount of space. Again, the easiest way of, again, going through Vesper is to just start drawing molecules and going from there. If you have a Lewis dot structure, I'm going to intentionally draw this weird, okay? I draw this like that. That is a correct Lewis dot structure, because a Lewis dot structure is connectivity. But does it represent the real structure of the molecule? It's physical. No. And the reason why is this represents two sets of electrons. Two electrons here, two electrons there. The way I've drawn it, it implies that they're at a right angle, right? But what we find is the repulsion between the pairs of electrons are so significant that they want to get away from each other as much as possible. So instead of being at 90 degrees, what's observed is we have a bond angle of 180 degrees, which would be linear geometry. By the way, as I'm going through Vesper geometry is based on repulsion of electrons. Sometimes Vesper will fail. And the reason why is, in some cases, the repulsion isn't actually as great as we might expect. And so the angle of the molecule, the bonds, are actually 90 degrees when you predict 180 or something like that. So as we go forward, we're going to see Vesper is a very good model to use, but it is not absolute. So again, this is where understanding more aspects of bonding are going to go forward. So we have linear. Let's say we have the chloro version, where we substitute one hydrogen. We'd also expect this to be linear. Again, should be about 180. Aside from the chemical composition, what is something else that is fundamentally different about these two molecules?
Low pairs.
You got low pairs, yes. Okay. That's more that it happens to be a chlorine. It's bigger. If I was looking at the physical properties of BeH2 versus BeClH, polarity, yes. When we look at molecules, one of the first things you should just kind of intuitively think about is the molecule polar or non-polar? And what you're really doing when you look at that is you're actually asking yourself, is the molecule symmetrical or asymmetrical? We'll be getting into what's called group theory, where we actually analyze the symmetry of the molecules in a more mathematical way, in a more rigorous way. So, beryllium and hydrogen have different electronegativities. Now, on the periodic table, we can, based on position, we can estimate the electronegativities. Even if we don't know exactly what they are, we can look them up. As long as we know that they're different, we can make a rationalization. Hydrogen is more electronegative than the beryllium. So the hydrogens are pulling on the beryllium. But they have equal magnitude, and they're pulling in opposite directions. So the net result is going to be 0. Right? It's a game of tug of war. You have two people pulling, but they're identical. So in this case, our molecule is nonpolar. But now with chlorine, chlorine is a halogen, so it's going to be more electronegative. Another one. So it's pulling in this direction with that magnitude. Hydrogen is pulling like that. In our game of tug of war, the chlorine is going to win. It's going to pull the electron density towards itself. As a result, we get a partial negative over here. And whether it's located on the hydrogen or beryllium doesn't matter, but I'll just put it on the hydrogen. Then we'll have a partial positive. So the little squiggly sign is lowercase delta. Right? So this is the, triangle is the capital letter delta. And then this little guy is also delta, but it means partial change. Whereas the capital version means full change. If you take this game of tug of war to an extreme and you keep pulling the electron density from one atom to another, let's say we pair up sodium with chlorine, what type of chemical bonding are we talking about? Ionic. Where it's nonpolar, it would be covalent or pure covalent. But in this case, we have charge separation. Chlorine is pulling electron density towards itself, so it becomes partially negative. Well, then the hydrogen or the beryllium must become partially positive in the equal magnitude. And this would be polar covalent. Or a polar molecule, right? What else has poles besides the Earth? Sneak that one in there before you can say it. What else has poles? Magnets. The molecule is acting completely analogous to a magnet. So in other words, if you put north and south on here, it's the same thing. And in fact, this is something that in your Chemistry 112 course, as you get to intermolecular forces, you have molecules that are polar, molecules that are nonpolar, and they behave differently, right? Water is polar, right? Whereas oils are nonpolar. Try and mix them together, oil and water don't mix, right? So you see these type of behavior, but it all comes back down to geometry and chemical composition of the molecules to explain this. So moving on, so we've got our two coordinate geometry. So if we just have two atoms, like oxygen, O2, you don't have a true geometry. To have a geometry, you need three atoms because it takes 3 points to define a line, right? So in other words, so that's why we start at a 3-atom system. So if I have BH3, borane, okay, 3 chemical bonds around it, each one is going to be symmetrical, so these bond angles are 120, so we're chopping up a 360 degrees circle, and this would be trigonal planar. And again, I'm reviewing all of this from Chemistry 111 right now because, again, if you haven't, if you don't remember this, now is the time to learn it. And just to save time, I'm not going to go through the substitutions of that for polar versus nonpolar, but we will do something like that. along with carbon monoxide, the question was asked, is carbon monoxide organic? Well, is methane organic? And obviously this is where organic chemistry starts, right? Because typically the real definition of organic chemistry is when we have carbon with hydrogen. So I was kind of playing around with that, making fun of organic chemistry. But really, when you start talking about organic chemistry the way it's taught in Chem 301, you have to have a carbon and at least one hydrogen bound to it. Then it falls in that category. So methane obviously would fit the bill. What do the bond angles look like here? 90 degrees. Which, if we were flat in a two-dimensional world, that'd be fine. But what we find is,
aren't they like 180? I mean 120?
not 120, 109.
108.
Yes. So hydrogen, 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 right? And this gets us, yes, to 109.5 degrees, the tetrahedron, or tetrahedral geometry, TD. And I will say definitively, this geometry is pure evil because it's very difficult to visualize. Things that are at right angles, 90 degrees, 180, all that, we have a much better intuition. We typically, you can find some examples, but you typically don't see buildings built based on the tetrahedron and so forth, just because of the weirdness. And this is one of the difficulties in organic chemistry, when you have a tetrahedron bound to another tetrahedron, bound to another tetrahedron. Visualizing this particular geometry can be tricky. And so we're going to see that is kind of our core. Now, we move away from organic chemistry, and now we're in the good stuff, inorganic. So no carbons. If we have PCl5, and by the way, I'm going to come back to this, of course, and we're going to go through orbital hybridization. SP, SP2, all of that, but I just want to get these geometries on board. 5-coordinate geometry, there's actually several different types of 5-coordinate geometry, but what you should have seen before is trigonal bipyramidal. The bond angles within the plane, this is 120 degrees. Above and below the plane, we have 90, or you could say 180 from the chlorine to the chlorine. I'm going to come back, I'm running out of time, so I'm going to come back to all of these geometries and do the derivations of them. Now, 6-coordinate, I'm going to leave off the lone pairs to save myself a few seconds. SF6, each of these angles is either 90 or 180. We have 6 things bound to the central atom. So it would be 6 something or hexa, but of course it's called octahedral. OH. What is octane? How many?
8.
8. Why is 6 8? And you can't say I never gave you anything. You can say I never gave you anything good. Let's pass these back. What I'm passing out right now, this is the tetrahedron. This around. And the second one, I printed them in the same color. This is an octahedron. And what you want to do with the octahedron, count the faces of the octahedron. Okay. You can also use these as your Dungeons and Dragon dice. Exactly, yes. When you have the solid geometry of SF6, It's octahedral geometry, which has 8 faces. There you go. I'm sure the tetrahedron is working its way around. So if I have a little octahedron, 4 faces on top, 4 faces on bottom. That's where this term octahedral comes from. You can blame solid geometry for it. A tetrahedron has 4 points, but it also has 4 faces. So the math works out easier from there. I want you to have these, and over time I'm going to be giving you more of these little models because this aspect of inorganic chemistry is very visual. And so being able to think in terms of octahedral geometry, just know what that means, or tetrahedral geometry and so forth, is going to be absolutely critical. So for an octahedron, your central atom, could be in this case sulfur, and then at each vertice, that's where the fluorines are. Right? So this is if the molecule was a solid thing. As chemists, we think about what's on the point, what's at the vertex, right? So again, that's where some of the nomenclature comes from. So did everybody get a tetrahedron and an octahedron? I have spares, so all right. Okay, so that's a good place to stop. If you haven't done so, keep reading through chapters 1 and 2. Try and get up to Vesper, because we're going to find Vesper does not stop at 6. So there'll be 7 and 8 coordinate geometries, good times. So, all right.
I stand by what I said. Look here.
Yes, and I'll be sending something out about the quiz tonight. So
Close enough.
sure.
You're an engineer, yes?
Yes, and you are, so what's the problem?
Well, we'll talk about that when we get to transition. Yeah. So right now, I just wanted to show you what it was. Yes.
So, since I asked, cells like acid and how would you do that?